Hi everyone, I am Waybase SB, Junior College Teacher, RBNB College, Sri Rampur. In today's lecture, we are going to start the new topic, line and plane. Line and plane. And this topic is for 10 marks with option in HSC board exam. In this topic, we have to see the equation of line as well as the equation of plane. So first we see the equation of line. So let's see the theorem first. The vector equation of a line passing through the point A with position vector A bar and parallel to vector B is R bar is equal to A bar plus lambda into B bar. So let's see the proof of this theorem. Let a line L passes through point A with position vector A bar and parallel to vector B. X origin, Y, Z. So your line is here. This is point A through which the line passes, and this is the vector which is parallel to the line. This is vector B. So this is A bar. Let P with R bar be a variable point. On the line other than A. So that point P is here with position vector R bar. If we join, so this is R bar. From the figure, AP bar is parallel to B bar. So therefore, AP bar is parallel to B bar. So we know that AP bar is parallel to B bar means AP bar and B bar are collinear vectors, and we know that if any two vectors are collinear, then any one of them can be expressed as the scalar multiple of other. So here we express AP bar as a scalar multiple of B bar. So therefore AP bar is equal to lambda into B bar, where lambda is scalar. So AP bar, this is the position vector of the point P minus position vector of the point A. So it is OP bar minus OA bar is equal to lambda into B bar. But from the figure, what is OP bar? R bar, and OA bar? A bar. So it is R bar minus A bar is equal to lambda into B bar. That is, so therefore shift this minus A bar to right hand side. So R bar is equal to A bar plus lambda into B bar. So this is the vector equation of a line passing through the given point and parallel to the given vector. So here remark, now in the vector equation of line we have R bar is equal to A bar plus lambda into B bar. This lambda is parameter and that parameter lambda corresponds a point on the line L, or every point on the line L corresponds a unique value of lambda. This equation R bar is equal to A bar plus lambda into B bar. This is called parametric vector equation. Parametric vector equation. Also see in the next remark, see vector AP is parallel to vector B. So AP bar is parallel to B bar, means AP bar and B bar are collinear. So therefore AP bar cross B bar is equal to 0 vector, because we know that if any two vectors are collinear, then their cross product is 0. So AP bar cross B bar is equal to 0. But what is AP bar? It is R bar minus A bar cross B bar is equal to 0 vector, and this is called non-parametric vector equation. See, the first one is parametric vector equation, and this is non-parametric vector equation of a line passing through the given point and parallel to the given vector. So let's see next theorem. Now in this theorem 2, we have to find out the equation of a line passing through the given point and having direction ratios. That means we have to find out Cartesian equation in theorem 2. So the Cartesian equation of a line passing through capital A, X1, Y1, Z1 and having direction ratios A, B, C is x minus x1 upon A is equal to y minus y1 upon B is equal to z minus z1 upon C. So let's see the proof. Let a line L passes through capital A with coordinates x1, y1, z1 and has direction ratios A, B, C. See, if this is the line which passes through a point A, x1, y1, z1. Let P with position vector R bar be any point on the line L other than A. So if that point P is here, this is the point P with position vector R bar, or if the point P with coordinates, because in this we have to study Cartesian equation. So here the point is P, X, Y, Z. Be any point on the line, so it is X, Y, Z. Now see, here the line L is in this space and we have two points on the line. So we can write the direction ratios of that line. The direction ratios of line L are x minus x1, y minus y1 and z minus z1. But the direction ratios of a line are ABC. But direction ratios of a line L are A, B, C. Now the line L has direction ratios x minus x1, y minus y1, z minus z1 as well as ABC. It means that they are in proportional. So therefore x minus x1 divided by A is equal to y minus y1 divided by B is equal to z minus z1 divided by C. This is the Cartesian equation of a line passing through the given point and having direction ratios A, B, C. Now we see the remarks. If A1, B1, C1 are direction ratios of a line, if in the Cartesian form direction ratios of a line are given, that are A1, B1, C1, then we know that the vector which is parallel to this line in vector form, that is B bar. So then B bar is equal to A1 I cap plus A2 J cap plus A1 I cap plus B1 J cap plus C1 K cap. See, if the direction ratios of a line are known, then we can write the vector which is parallel to the line. Or if we know the vector parallel to the line, then the direction ratios of line also given. So conversely, if B bar is equal to A1 I cap plus B1 J cap plus C1 K cap, then direction ratios of a line are A1, B1, C1. See, in the first remark, if direction ratios of a line are given, then we can write the vector B, means vector parallel to the given line. Or if vector parallel to the given line is known, then we can write the direction ratios of a line. In the second remark, the equation x minus x1 divided by A is equal to y minus y1 divided by B is equal to z minus z1 divided by C is equal to lambda. This is called symmetric form of equation of a line, किंवा symmetric form of Cartesian equation. This equation of a line is called the symmetric form of Cartesian equation of line. See, from this equation, if we compare first and last term, so x minus x1 is equal to a lambda. X minus x1, see, x minus x1 is equal to a lambda. So shift this minus x1, so x is equal to x1 plus a lambda. Similarly, y is equal to y1 plus b lambda. And if we compare the last two, then z is equal to z1 plus c lambda. So therefore the equations x is equal to x1 plus a lambda, y is equal to y1 plus b lambda, and z is equal to z1 plus c lambda are called parametric form of Cartesian equation. Parametric form of Cartesian equation of a line. So now this is symmetric form of Cartesian equation of a line, and this is parametric form of Cartesian equation of a line. Here, if ABC are direction ratios of a line, if ABC are non-zero, none of them is 0, at that time use symmetric form. If at least one of the direction ratios of a line is 0, then use parametric form of Cartesian equation of a line. Next remark, the coordinates of variable point P are, see here in this equation, x is equal to x1 plus a lambda, y is equal to y1 plus b lambda, and z is equal to z1 plus c lambda. What are x, y, z? X, y, z are the coordinates of point P. So from this remark, the coordinates of a variable point P are x1 plus a lambda, y1 plus b lambda, and z1 plus c lambda. Now, if direction ratios are known, then these are the coordinates of a variable point P on the line L. If direction cosines are known, if L, M, N are direction cosines of a line, then coordinates of P are x1 plus L lambda, y1 plus m lambda, comma z1 plus n lambda. See, this is the line which is in the space. The point P is here, whose coordinates are x1 plus L lambda, y1 plus m lambda, and z1 plus n lambda. And point A is here, whose coordinates are x1, y1, z1. So, 2 points in the space are known, so we can find the distance between them, and distance between A and P is AP. It is equal to square root of, so if we take the square of AP, that is AP square, then square root get cancelled. So it is equal to, in bracket, see, here use the formula x2 minus x1 bracket square plus y2 minus y1 bracket square plus z2 minus z1 bracket square. So it is equal to x1 plus L lambda minus x1 bracket square plus y1 plus m lambda minus y1 bracket square plus z1 plus n lambda minus z1 bracket square. So it is equal to x1 minus x1 0. So it is L lambda square plus m lambda square plus n lambda square. So it is equal to L square lambda square plus m square lambda square plus n square lambda square. It is equal to, take lambda square common from these three terms. So it is lambda square in bracket L square plus m square plus n square it is equal to. Now, what are LMN? LMN are direction cosines of a line. So, we have one of the property of direction cosines of a line, that is L square plus m square plus n square is equal to 1. So, lambda square in bracket 1. So, therefore, it is equal to, what is this? AP square. So, AP square is equal to lambda square. So, from this one, AP is equal to modulus of lambda. So what is lambda? Lambda is parameter, and that parameter lambda gives us the distance of AP. A is known, P is variable point. So this lambda gives us the distance of a variable point on the line from the base point. So AP is equal to modulus of lambda, or if we remove the modulus sign, remove the positive value, so it is lambda is equal to plus or minus AP. So remember, what is lambda? What is parameter? Parameter gives us the distance of a variable point P on the line L from the base point A. So this is everything about the Cartesian equation of a line passing through the given point and having direction ratios. So let's see next theorem. Now theorem 3. The vector equation of a line passing through 2 points A with position vector A bar and point B with position vector B bar is R bar is equal to A bar plus lambda into B bar minus A bar. So proof. See here we have a line which passes through 2 points, A with position vector A bar and B with position vector B bar. So let a line L passes through point A with position vector A bar and point B with position vector B bar. So we have a line in the space which passes through 2 points. This is three-dimensional system. We have a line passing through 2 points A and B, A with position vector A bar and point B with position vector B bar. So if we join OA and OB, we get the position vectors of the point A and B. So it is A bar, this is B bar. Let P with position vector R bar be any point on the B any means here we particularly write this point P with position vector R bar as variable point. So let P with position vector R bar be variable point on the line other than A. So if this point P is here with position vector R bar, join OP, so it is R bar. So now from the figure, AP bar and AB bar lies on the same line. Therefore, the vectors AP bar and AB bar lies on the same line. It means they are collinear. And we know that if any two vectors are collinear, if any two vectors are parallel, then any one of them can be expressed as the scalar multiple of other. Here AP bar and AB bar are collinear, so AP bar can be expressed as the scalar multiple of AB bar, or AB bar can be expressed as the scalar multiple of AP bar. So here we write AP bar as a scalar multiple of AB bar, where lambda is scalar. So therefore, what is AP bar? Position vector of the point P minus position vector of the point A. So it is OP bar minus OA bar is equal to lambda into AB bar. This is nothing but OB bar minus OA bar. So OP bar, it is R bar minus A bar is equal to lambda into OB bar position vector of the point B, that is B bar, OA bar position vector of the point A, that is A bar. So r bar minus a bar is equal to lambda into b bar minus a bar. Shift this minus a bar to right hand side. So we get r bar is equal to a bar plus lambda into b bar minus a bar. So r bar is equal to a bar plus lambda into b bar minus a bar. This is the vector equation of a line. Now in this equation, lambda is present, lambda is parameter, so this equation is also called as parametric vector equation of a line. This equation is also called as parametric vector equation of a line. Remark: the equation r bar is equal to a bar plus lambda into b bar minus a bar is called parametric vector equation of line. Second remark: see here, if you observe the figure, AP bar is parallel to AB bar. So AP bar is collinear with A bar. So the cross product of AP bar and AB bar is 0 vector. See, AP bar is collinear. Okay, AP bar, comma AB bar are collinear. So therefore, AP bar cross AB bar is equal to 0 vector. It means R bar minus A bar cross B bar minus A bar is equal to 0 vector, and this equation is called non-parametric vector equation. This equation is called, or this is called non-parametric vector equation of a line. So this is called parametric vector equation, and this equation is called non-parametric vector equation, because in this equation parameter is absent, so that's why it is non-parametric, and in this equation parameter is there, that is lambda, so it is called parametric vector equation. So we see next theorem, theorem number 4. The Cartesian equation of a line passing through two points, capital A, x1, y1, z1, and capital B, x2, y2, z2 is x minus x1 divided by x2 minus x1 is equal to y minus y1 divided by y2 minus y1 is equal to z minus z1 divided by z2 minus z1. So let's see the proof. Here we have given a line passing through 2 points, and that 2 points has Cartesian coordinates. Let a line EL passes through A, x1, y1, z1 and B, x2, y2, z2. If you draw the figure, this is three-dimensional system. X-axis, origin, y-axis and z-axis. Your line is here. And point B is x2, y2, z2. Let P with coordinates x, y, z. Whenever we prove the Cartesian equation, at that time variable point is p, x, y, z, or whenever we prove the vector equation, at that time take the variable point p as p with position vector r bar. Now here Cartesian, so we have to take p with coordinates x, y, z, means we have to take point p with Cartesian coordinates x, y, z, be a variable point on the line L other than A, so point P is here whose coordinates are x, y, z. Now first consider only these 2 points A and B. With the help of these 2 points, the direction ratios of line L, direction ratios of line L are x2 minus x1, y2 minus y1, z2 minus z1. Because we know that if a line contains or line passes through 2 points a x1, y1, z1 and b x2, y2, z2, then its direction ratios are x2 minus x1, y2 minus y1, z2 minus z1. But direction ratios of a line L are, see, if we consider the 2 points A and B, then direction ratios of this line L are x2 minus x1, y2 minus y1, z2 minus z1. Now consider the 2 points A, x1, y1, z1 and point P, x, y, z. These are also 2 points on the same line L, and we know that if we have 2 points on the line, any line, then we can write the direction ratios of that line. So A is x1, y1, z1, and suppose point P, that is x2, y2, z2, means x2 is x, y2 is y and z2 is z. So using the same definition, the direction ratios of a line L are x minus x2 minus x1 means x minus x1, y minus y1, z minus z1. Now these are direction ratios of the same line L, so they are in proportional. So therefore x minus x1 upon x2 minus x1 is equal to y minus y1 upon y2 minus y1 is equal to z minus z1 divided by z2 minus z1. This is the required Cartesian equation of a line passing through 2 points A, x1, y1, z1 and B, x2, y2, z2. Actually, the Cartesian equation of a line is not a single equation. These are equations of, because if you compare x upon this first term and if it is equal, take some constant, so we get first equation. If we compare second and last one, we get second equation. So actually this is not a single equation, these are equations of a line. So today we have seen equation of line passing through the given point and parallel to the given vector, also equation of line passing through 2 points. Now in the next lecture we will see the examples from exercise 6.1.